Okay, so today we continue our discussion of the spectral theorem for bounded operators on a Hilbert space. Well, let's recall that the spectral theorem is not a single theorem, but is rather a collection of results closely related to each other and describing the structure of operators, of normal operators on a Hilbert space. And as the previous lecture, we began to discuss one of these results, which states that each normal operator has a functional model. So to recall what was actually proved at the previous lecture, and also to understand what still has to be done, let's look at the following table. Well, first of all, we observed at the previous lecture that sometimes it is convenient, instead of working with normal operators, it is convenient to consider more general objects, namely star representations of algebras of continuous functions, C of x, or equivalently star modules over C of x. So this will be the first column in our table, and the second column corresponds to normal operators. So if we prove something about star representation of C of x, then we immediately get a corollary about normal operators. And the reason is that if X is not an arbitrary compact space, but a compact subset of the complex plane, then we have a one-to-one correspondence between normal operators whose spectrum is contained in X and the star representations of C of x. And this correspondence is given by the functional calculus, by the continuous functional calculus for the operator. Okay, and at the previous lecture we discussed the special case of cyclic modules, which correspond to star cyclic operators. And we proved the following result, namely if H is a cyclic star module over C of x, then H is unitarily isomorphic to the module L2 of x, mu, for some positive finite Radon measure on X. So the action of C of x on L2 of x is just the pointwise multiplication. And in the case of operators, this gives us the following result. If we have a star cyclic normal operator T on a Hilbert space, then T is unitarily isomorphic to a very concrete operator, the multiplication operator MT, which acts on the L2 space on the spectrum with respect to a finite positive Radon measure mu. And MT is nothing but the multiplication by the coordinate. So it acts by the following formula. So if I'm not mistaken, this was theorem 1 at the previous lecture, and this corollary was theorem 2. Okay, this is already done. These are the functional models for a star cyclic module over C of x and for a star cyclic normal operator. And today we discuss the general case. So the result will look as follows. If H is an arbitrary star module over C of x, then H is unitarily isomorphic to the following module, L2 omega mu. And the subscript phi refers to a specific function. So omega mu is a measure of space. Now it is not necessarily finite, and actually it is not necessarily sigma finite. And phi is a measurable map from omega to x. Measurable map. And the action of C of x on the space is given by the following formula. So if A is a continuous function on x and f is in the space, then the action of A on f is the pointwise product of A phi and f. Here A is a continuous function and f is in the big O2 space. So this will be our goal. And after we prove this, as a corollary, we will get the following result. If T is a normal operator on the Hilbert space, then T is unitarily equivalent to the multiplication operator M phi, which acts on the big L2 space, L2 of omega mu, by the following simple formula. Just the pointwise multiplication by phi. Here phi is a bounded measurable function on omega. Okay, so once again, the first row is already done, and the second row is our goal. So this is what we are going to prove today. Okay, so we start with the following simple lemma. Lemma 1. Suppose that A is a Banach star algebra and H is a star module over A. And suppose that H0 is a submodule of H. I claim that the orthogonal complement of H0 is also a submodule. So the orthogonal complement of a submodule is also a submodule. The proof is just a line. So we take an element in A, an element x in the orthogonal complement, and an element y in H0. So what we want to do is to show that AX is still in the orthogonal complement. In other words, we want to show that this inner product is 0. Okay, but why is it 0? We recall the one of the axioms of a star module. We move A from here to here. So this will be the inner product of x and A star y. Now, H0 is a submodule, so this element sits in H0. And since x is in the orthogonal complement, this is 0. And that's it. So this shows that AX belongs to the orthogonal complement. Okay, now lemma 2. Lemma 2 states that each star module is isomorphic to a Hilbert direct sum of cyclic submodules. So we suppose that A is a Banach star algebra, and H is a star module over A. Then there exists a family, Hi, of pairwise orthogonal cyclic submodules of H such that H is isomorphic to their Hilbert direct sum. The proof of lemma 2 is a standard argument based on Zorn's lemma. So we consider the following set. Let's denote it by M. This is the set of all families of non-zero, pairwise orthogonal, cyclic submodules. Cyclic submodules of H. Clearly, this is a partially ordered set. So the order relation is just the inclusion. And it's very easy to show that this set satisfies the conditions of Zorn's lemma. This is a very easy exercise for you. So by Zorn's lemma, it has a maximal element. Let's take maximal element and let's denote it by the family H. Let this family be the family HI. So let HI be a maximal element. Of M. So I claim that this is exactly the family we are looking for. And to see this, let's denote by, say, L, the quarter of their algebraic sum. The quarter of the algebraic sum. So actually, we want to show that L equals H. This will mean exactly that H is the Hilbert direct sum of the family HI. Well, why is it so? Well, suppose that this is not the case. Suppose that L is strictly smaller than H. So the orthogonal complement is non-trivial. And let's take an arbitrary element, an arbitrary non-zero element in the orthogonal complement. So we take an arbitrary element in the orthogonal complement, and we look at the following family. We take our original family HI, and we add one element, namely the cyclic submodule generated by X. So what can you say about this family? I claim that this family is still in M. And this follows from lemma 1. Well, indeed, X is in the orthogonal complement. So the orthogonal complement is a submodule. And so the cyclic submodule generated by X is contained in the orthogonal complement of L. So this cyclic submodule is orthogonal to any HI. And so this is also a family of pairwise orthogonal cyclic modules. But this is a contradiction. This is a contradiction because by assumption this was a maximal family. And this one is strictly bigger. So this contradiction shows that L is nothing but H, and this means that H is the Hilbert direct sum of the family Hi. Okay, so this completes the proof. And now we are ready to prove the functional model theorem about, for star representations. So this will be theorem 3. A functional model for star representations of C of x. So suppose that X is a compact Hausdorff topological space. And H is a star module over C of x. Then there exists a measure space, omega mu, and a measurable map phi from omega to x. So when I say measurable, I mean that we consider x as a measurable space with respect to the Borel sigma algebra. So this means that the preimage of each Borel set sits in the sigma algebra of our measure space omega mu. Such that H is unitarily isomorphic to L2 of omega mu phi. Of course, unitarily isomorphic over C of x. So the definition of this module is given here. Okay. So to prove this result, we first of all combine theorem 1 from the table with lemma 2. So by lemma 2, H is a Hilbert direct sum of cyclic modules. And each of the cyclic modules is isomorphic to L2 of x mu for a suitable measure. So this implies that H is unitarily isomorphic to the Hilbert direct sum of L2 of x mu I, where each mu I is a positive Radon measure on X. And now, to construct our measure space omega mu, we combine these pieces together in the following way. First of all, we define omega as a set. So omega will be the product of X and I. It will be convenient to interpret this set as the disjoint union of many copies of the same space X. So each xi equals X. This is another way of looking at the product. The next step is to define a sigma algebra of subsets of omega. So the sigma algebra A will consist of all disjoint unions Bi, where each Bi is a Borel subset of Xi. So clearly this is sigma algebra. Now we have to define a measure, mu, on the sigma algebra. And the definition is pretty straightforward. So we define mu on this set, the disjoint union of Bi, to be the sum are the measures of Bi. This can be finite or this can be infinite if the series diverges. So in general, the measure mu is not finite. Okay, so this is from our measure space. Now we have to construct a measurable map phi. So we define phi from omega to x as follows. It takes each pair xi, so we recall that omega is the product of x and I. So it takes xi to x. And clearly, this is a measurable map. So to understand this better, let's draw a picture. So suppose that our set I is at most countable, and that x is, for example, an interval of the real line. Then omega looks as follows. So this is the joint union of most countably many copies of x. And well, this is the graph of our function phi. So this is an illustration. Okay, so now we have to construct a unitary isomorphism between L2 of omega mu, between this module and the module H. And to construct such an isomorphism, we do the following. So for each element I in our index set, we let Hi denote the space of those functions f in the big L2 space on omega such that f is concentrated on xi. In other words, f is 0 almost everywhere on the complement of xi. Okay, so clearly Hi is a closed submodule. This is a closed submodule. And moreover, this submodule is unitarily isomorphic to L2 of x mu I or C of x. The isomorphism is obvious. We just take a function in here. So it is already defined on the ith copy of our space. And we extend it by 0 outside xi. And the result will sit in the module Hi. So clearly, this is unitary isomorphism between these two modules for the simple reason that the measure mu restricted to the ith copy of x is nothing but the measure mu I by the very definition of our measure. Okay. Now, it's also clear that these modules are pairwise orthogonal. Hi is orthogonal to Hj whenever I is not equal to j. This is clear. And let's show that the sum of these submodules Hi is dense in L2. Well, if, for example, we have a function f which is orthogonal to each Hi, then this means that if we fix I, then this orthogonality condition means that f vanishes on xi. Almost everywhere. And this happens for each I. But if we look again at the definition of our measure, this means that f is 0 almost everywhere on omega. And so this implies that the orthogonal complement of the algebraic sum of the family Hi is trivial. Or in other words, this means that this sum is dense in L2. Okay, so this is almost the end of the proof. So this algebraic sum is dense in L2. So this implies that L2 is isomorphic to the Hilbert-Direct sum, L2 of omega mu. Phi is unitarily isomorphic to the Hilbert-Direct sum of the modules Hi. Now we recall that each Hi is isomorphic to L2 of x mu I. So we can write the following unitary isomorphism. And this is our original module H. That's it. So we get the required isomorphism. Well, let's just look at the definition. So we take a Borel subset in here. So what is the preimage? The preimage will be the disjoint union of this many copies of the same Borel set.
But what if it's in some it's not
Well, we'll look at the definition of our sigma algebra. Our sigma algebra consists exactly of such infinite disjoint unions. So we take an element by definition, a subset of A is measurable if it can be written in this form. This is the definition of our sigma algebra. So if we take
so if we don't claim that this sum is finite.
No, this is an arbitrary disjoint union. In each copy, we take a Borel set. So it can happen that I is uncountable. So we have uncountably many copies of uncountably many Borel sets. But just by the very definition of A, such a set will be measurable. So the point is that I don't claim that omega in A corresponds to any topological space. So omega is not a topological space, and A is not a Borel sigma algebra. So omega is just a set. We don't introduce any topology on omega, and A is just a sigma algebra. And so we define it in such a way that phi becomes measurable. Okay. So as a special case, we obtain theorem 4, which gives us a functional model of a normal operator. And this is our first form of the spectral theorem. If H is a Hilbert space, and T is a bounded normal operator on H. Then there exists a measure space omega mu, and a bounded measurable function phi on omega, such that T is unitarily equivalent to the multiplication operator m phi, which acts on the space L2 of omega mu, and it acts by the following simple formula. That's the pointwise multiplication by phi. Well, this is a simple corollary of theorem 3, because we just recall that T has a continuous functional calculus, and the continuous functional calculus is a star representation of the algebra of continuous functions on the spectrum. And so H becomes a star module over the algebra of continuous functions. Okay. Many people believe that actually this result is the optimal form of the spectral theorem. Well, indeed, this result has the advantage of being very concrete and understandable. And actually, all the essential information about a normal operator can be deduced from its functional model. The disadvantage of this form of the spectral theorem is that the functional model is not canonical in any reasonable sense. And the reason for that comes from the fact that the construction of the measure space omega mu involves a decomposition of H into a Hilbert-Dirac sum of cyclic submodules. This decomposition is not unique. Now our next goal will be to prove another form of a spectral theorem, which is formulated in terms of the Borel functional calculus. Spectral theorem 2, the Borel functional calculus. Okay, so to formulate this theorem, we need some preparation. Because the statement, the definition of the Borel functional calculus involves two specific locally convex topologies, namely the weak measure topology and the weak operator topology. So as the first step, let's define these topologies. So we start with the weak measure topology. So we take a compact Hausdorff topological space X, and we denote by B of X the space of all bounded Borel functions. Bounded Borel functions on X. So clearly this is a Banach space with respect to the supremum norm. Actually this is a Banach algebra, and actually this is a C-star algebra, but at this point this is not very important for us. And also we take the, as usual we denote by M of x, the space of complex Radon measures, which is also a Banach space. There is a canonical pairing between these spaces given by integration. So we denote by the symbol, the integral of f with respect to mu. Here f is a bounded Borel function, and mu is a finite Radon measure. It's a complex Radon measure on x. It's very easy to see that this form makes B of x and M of x into a dual pair. Proposition 1, B of x and M of x form a dual pair of vector spaces. The proof is a very, very simple exercise in measure theory. It's almost immediate from the basic properties of the integral. Okay, we now define the weak measure topology. The weak measure topology WMT for short on the space B of x to be the weak topology corresponding to this dual pair. So, in other words, this is topology. This topology is generated by the following family of seminorms. So each seminorm is indexed by a Radon measure, mu, and is defined to be the absolute value of the integral of f with respect to mu. So I'd like to stress, just in case, that we integrate f and then take the absolute value. So this is different from the L1 norm, where we integrate the absolute value of f. Okay, so B of x becomes a locally convex space with respect to the weak measure topology. And we have the following result, proposition 2. C of x, the space of continuous functions, is dense in B of x. Well, strictly speaking, this is false, because B of x is by default equipped with the supremum norm, and C of x is a closed proper subspace in B of x. But it will be dense if we equip B of x with a weak measure topology. The proof is a standard application of the duality theory for locally convex spaces. Namely, we have the canonical map from M of x to the dual of C of x, which takes each measure to the respective integral. And this map is injective. And in fact, this result is the easy part of the Riesz-Markov-Kakutani theorem. So the Riesz-Markov-Kakutani theorem states that this map is an isometric isomorphism. So the difficult part of this theorem is the surjectivity of this map. But at this point, we use only the injectivity. So this map is injective. This implies the following. If we consider C of x as a subspace in B of x, and we take the annihilator with respect to this to the dual pair, then the annihilator is 0. The annihilator is taken with respect to the dual pair B of x, M of x. So in other words, this means that if we have a measure such that the integral, the measure mu such that the integral of any continuous function with respect to mu is 0, then the measure is 0. So this means that the annihilator of C of x is 0. But it follows from the standard, this is one of the standard results of the duality theory, which was proved a few lectures ago, that in this case, this means precisely that this subspace is dense with respect to the weak topology. So what is the annihilator? So C of x sits here, in here. So the annihilator consists of all those measures mu, such that the integral of any continuous function with respect to mu is 0. Okay? But we know that this map is injective. So if mu determines a functional on C of x which is identically 0, then mu is 0. And this means exactly that the annihilator is 0. Okay, and so we conclude that the weak measure, the closure with respect to the weak measure topology is the whole space B of x. This is a corollary of the double annihilator theorem. Okay. Let's now show that, let's now recall that B of x is actually an algebra with respect to the pointwise multiplication. So now let's now show that the pointwise multiplication on B of x is compatible with a weak measure topology. So we need the following definition. By definition, a locally convex algebra. A locally convex algebra is an algebra, A, equipped with a locally convex topology. Such that the multiplication of this algebra is separately continuous. Separately continuous means that for each element A in our algebra, the multiplication maps from A to itself. So actually we have two maps. The first one is the left multiplication map, and the second one is the right multiplication map, are continuous. So this condition in brackets means exactly that the multiplication is separately continuous. Well, maybe it's natural to ask why separate continuity. It would be more natural to require that the multiplication is continuous as a map from A cross A to A. The answer is that if we require the usual continuity, the joint continuity, then we must throw away many natural examples of locally convex algebras. And this is not convenient for us. Okay, and we define a locally convex star algebra. A locally convex star algebra to be a locally convex algebra. Together with a continuous involution. Continuous involution on A. As usual, by an involution, I mean an algebra involution. That is a map which is antilinear, a ring anti-homomorphism, and an involution in the set theoretic sense. So now I claim, this is our next proposition, proposition 3, I claim that if we equip B of x with a weak measure topology, then this is a locally convex star algebra. To prove this result, well, let's introduce some notation. So for each bounded Borel function f, and for each complex Radon measure mu, we define a Borel measure f mu, f dot mu, by the following formula. F mu of B, where B is a Borel set, will be the integral of f over B with respect to mu. So it's immediate from the general properties of the integral that this is indeed a Borel measure, a sigma additive Borel measure. And moreover, it satisfies the following conditions. And this is a simple exercise in measure theory. That first of all, if we evaluate this on an arbitrary Borel set B, so this is less than or equal to the supremum norm of f multiplied by the variation of mu of B. And this implies, 2 follows from 1, that f mu is also a Radon measure. So the regularity condition on this measure follows from this estimate and from the regularity condition on mu. On mu. And property 3, if we have 2 bounded Borel functions f and g, then the integral of their product with respect to mu equals to the integral of g with respect to the measure f mu. To prove this, we just take, we check this condition in the case where g is a simple function, and then use the fact that the simple functions form a dense subspace in B of x. Okay. Now, we want to show that the multiplication is separately continuous. Well, okay, what we do, we take the product of 2 bounded Borel functions, and we calculate the respective seminorm on their product. So what is this? This is the absolute value of this integral. But because of this equality, this is the seminorm of g corresponding to the measure f mu. This follows from 3. But if we now recall the general continuity criterion for a linear operator between locally convex spaces, this means that this implies that the operator which takes g to fg, this operator is continuous with respect to the weak measure topology. And since the algebra is commutative, this implies that this is a locally convex algebra. And finally, the continuity of the involution readily follows from the following formula. So the involution is the complex conjugation. So this is the integral of the absolute of f bar over mu, and then we take the absolute value. But this is nothing but the seminorm of f corresponding to the complex conjugate measure mu bar. And again, this easily implies that the involution is continuous. And this completes the proof. So this is a locally convex star algebra. By the way, it's a nice exercise. Well, maybe it is not directly related to our course. It's rather an exercise, but well, maybe somehow it's somehow related because it is about locally convex spaces. The multiplication in general is not jointly continuous. In general, the multiplication on B of x with respect to the weak measure topology is not continuous as a map from the product B of x cross B of x to B of x. In effect, it is never continuous except for the case where x is finite. By the way, another useful exercise describes the convergence of sequences in this space. So a sequence Fn converges to F with respect to the weak measure topology, even only if it is uniformly bounded. Uniformly bounded, and converges pointwise. Fn of x converges to f of x for each x. A hint to this exercise is to use two fundamental results, namely the Banach-Steinhaus theorem and the Lebesgue-dominated convergence theorem. By the way, the second exercise implies that the multiplication is sequentially jointly continuous. So if Fn converges to F and Gn converges to G, then Fn Gn converges to Fg. But this holds only for sequences. And this doesn't apply the continuity in the usual sense. Okay, let's now discuss the weak operator topology. The weak operator topology is defined on the algebra of bounded operators on the Hilbert space. In fact, the algebra of bounded operators on the Hilbert space has many useful topologies, and the weak operator topology is only one of them. So we give the following definition. Suppose that H is a Hilbert space. We define the weak operator topology WOT for short on B of H to be the locally convex topology generated by the following family of seminorms. So the seminorms are indexed by pairs of vectors, say U and V in H. And they are defined as follows. The seminorm of T corresponding to U of V, U and V, is the absolute value of the following inner product, Tu and V. Okay, we now have the following proposition. Proposition 4. B of H, the algebra of bounded operators, equipped with the weak operator topology, is a locally convex star algebra. The proof is almost immediate from the definition. If we take two bounded operators, S and T, and if we calculate the seminorm of their product corresponding to U and V, so what is this? This is the absolute value of S, T, U, the inner product of S, T, U, and V. And this is nothing but the seminorm of S corresponding to T, U, and V. And our general criterion of continuity for an operator between locally convex spaces implies that the operator which takes S to ST is continuous with respect to the weak operator topology. So this is the continuity of multiplication with respect to the first variable. But BOH is not commutative, of course, so we still have to show that the multiplication is continuous with respect to the second variable. And to show this, we write this expression in a slightly different form. Namely, we move S from here to here. So this will be the inner product of TU and S star V. And this is the seminorm of T corresponding to the vectors U and S star V. And this equality implies that the map which takes T to ST is also continuous for the weak operator topology. And this completes the proof. And again, a useful exercise is to show that if H is infinite dimensional, then the multiplication is not jointly continuous. So this is not continuous as a map from the product of BOH by itself to BOH. So this exercise and also this exercise show that our definition of a locally convex algebra is reasonable. So in general, we cannot claim that multiplication is jointly continuous. Okay, now I can explain what a Borel functional calculus is. So this is step 2, the definition of the Borel functional calculus. Suppose that H is a Hilbert space and T is a normal operator on H. Suppose also that K is a compact subset of the complex plane. And let's denote by little t. As usual, we denote by little t the inclusion map of K into the complex plane. By definition, a Borel functional calculus for the operator T on K is a continuous unital star homomorphism. Let's denote it by gamma or gamma T. from the algebra of bounded Borel functions on K to the algebra of bounded operators on H. And here we require the continuity with respect to the weak measure topology and the weak operator topology on B of H. A continuous unital star homomorphism such that gamma takes the inclusion map T to our operator big T. So if we compare this definition with our definition of a continuous functional calculus, we see that the difference in here. So in the definition of a continuous functional calculus, we require the continuity with respect to the norm topologies on the algebra of continuous functions and on B of H. And here we replace C of K with the bigger algebra of Borel functions, and we introduce another topologies on these algebras. This is very important. Let's look at some basic properties of the Borel functional calculus. So suppose that gamma is a Borel functional calculus for T on K. Then we have the following results. First of all, gamma will be continuous with respect to the norm topologies on B of K. So we have the supremum norm, the usual supremum norm of B on B of K, and the usual operator norm on B of H. And gamma is continuous. And this is immediate from the fact that each star homomorphism between C-star algebras is automatically continuous. Each unital star homomorphism between unital C-star algebras is continuous. This was proved some time ago. Second, if we restrict gamma to the algebra of continuous functions, then this restriction will be a continuous functional calculus. For T on K. Well, this is immediate from the definition of the continuous functional calculus. Part 3, the spectrum of T is necessarily contained in K. And this follows from part 2. So some time ago we proved that if there is a continuous functional calculus for T on K, then the spectrum is contained in K. And finally, part 4, gamma is unique. Well, why is it unique? Well, we know that the continuous functional calculus is unique. And we also know that C of K is dense in B of K with respect to the weak measure topology. So the density of C on K in here implies that gamma is unique. It turns out that this condition 3 is not just necessary, but it's also sufficient for the existence of the Borel functional calculus. And this will follow from the following general result about representations of the algebras of continuous functions. Well, let it be theorem 1. This is our first theorem about the Borel functional calculus. So suppose that X is a compact Hausdorff topological space. And let pi be a star representation of C of X on a Hilbert space H. I claim then there exists a unique continuous star representation pi tilde from the algebra of Borel, of bounded Borel functions on X, equipped with the weak measure topology, to the algebra of operators, BOH, equipped with the weak operator topology, such that pi tilde extends pi. In other words, each star representation of C of x uniquely extends to a star representation of B of x, which is moreover continuous with respect to these weak measure topology and the weak operator topology. And as a special case of theorem 1, we get theorem 2 about the Borel functional calculus for a normal operator, which is our second form of the spectral theorem. If T is a normal operator on a Hilbert space H, then for each compact subset K of the complex plane, which contains the spectrum, there exists a unique Borel functional calculus. For T on K. So theorem 2 follows from theorem 1. If we apply theorem 1 to the continuous functional calculus. So now the existence of the Borel functional calculus is reduced to theorem 1. So our first goal at the next lecture will be to prove theorem 1. And that's all for today. Да, ну я надеюсь, что следующая лекция будет. Как-то до сих пор у нас пока нету программы, этой самой программы экзаменов. Что-то вроде обещали прислать из учебной части, так до сих пор пока не прислали. Вот, но вроде я там